charge, positive there, is plus, and at that same plate, if you have your Gaussian surface at the top, you have the negative charge, Q induced. And so therefore, Gauss' law simply means that you have to take both into account. And so therefore, you can write down 1 over epsilon 0 times the sum of Q free. But now you have to make sure that you take the induced charge into account, and therefore you divide the whole thing by kappa. Then you have automatically taken the induced charge into account. So you can amend Gauss' law very easily by this factor of kappa. The dielectric constant is dimensionless, as I mentioned already. It is 1 in vacuum by definition. 1 atmosphere gases typically have dielectric constant just a hair larger than 1. We will most of the time assume that it is 1. Plastic has a dielectric constant of 3, and glass, which is an extremely good insulator, has a dielectric constant of 5. If you have an external field that can induce dipoles in molecules, but there are substances, however, which themselves are already dipoles, even in the absence of an electric field. If you apply now an external field, these dipoles will start to align along the electric field. We did an experiment once with some grass seeds, perhaps you remember that. And as they align in the direction of the electric field, they will strengthen the electric field. On the other hand, because of the temperature of the substance, these dipoles, these molecules which are now dipoles by themselves, through chaotic motion, will try to disalign. Temperature is trying to disalign them. So it is going to be a competition on the one hand between the electric field which tries to align them and the temperature which tries to disalign them. But if the electric field is strong, you can get a substantial amount of alignment. Permanent dipoles, as a rule, are way stronger than any dipole that you can induce by ordinary means in a laboratory. And so the substances which are natural dipoles, they have a much higher value for kappa, a much higher dielectric constant than the substances that I just discussed, which themselves do not have dipoles. Water is an example, extremely good example. The electrons spend a little bit more time near the oxygen than near the hydrogen, and water has a dielectric constant of 80. That's enormous. And if you go down to lower temperature, if you take ice of minus 40 degrees, it is even higher. Then the dielectric constant is 100. I'm now going to massage you through 4 demonstrations, 4 experiments. One of them you have already seen. And try to follow them as closely as you can, because if you miss one small step, then you miss perhaps a lot. I have 2 parallel plates which are on this table, as you have seen last time. And I have here a current meter. I put it an A in there, that means amp meter. And the plates have a certain separation G. I'm going to charge this capacitor up by connecting these ends to a power supply. And I'm going to connect them to 1500 volts. I'm already going to set my lights because that's where you're going to see it very shortly. I'm going to start off with a distance d, so this is going to be my experiment 1, with a distance d of 1 millimeter. And the voltage, V always means the voltage, the potential difference between the plates is going to be 1500 volts. Forgive me for the 2 V's, I can't help that. This means here the potential difference, and this is the unit in volts. Once I have charged them, I disconnect, this is very important, I disconnect the power supply, for which I write PS. That's it. So the charge is now trapped. As I charge it, as you saw last time, you will see that the ammeter shows a short surge of current. Because as I put charge on the plates, the charge has to go from the power supply to the plates, and you will see a short surge of current. which will make the handle, the hand of the amp meter, as you will see on the wall there, go to the right side, just briefly, and then come back. This indicates that you're charging the plates. And now I'm going to open up the gap. So this is my initial condition. There's no dielectric. And now I'm going to go D to 7 millimeters. And this is what I did last time. The reason why I do it again, because I need this for my next demonstration. If I make the distance 7 millimeters, then the charge, which I call now Q3, but it is really the charge on the plates, is not going to change. It is trapped. So there can be no change when I open up the gap. That means the amp meter will do nothing. You will not see any charge flow. The electric field E is unchanged. Because E is sigma divided by epsilon 0. If Q3 is not changing, sigma cannot change. So, no change in the electric field. But the potential V is now going to go up by a factor of 7. Because V equals E times D. E remains constant, D goes up, V has to go up. And this is what I want to show you first, even though you have already seen this. And I need the new conditions for my demonstration that comes afterwards. I'm going from 1500 volts to about 10,000 volts. It goes up by a factor of 7. And you're going to see that there. There you see your amp meter. I'm going to, you see this is this propeller voltmeter that we discussed last time. And here you see the plates. They're 1 millimeter apart now, very close. And I'm going to charge the plates. I will count down so you keep your eye on the amp meter. 3, 2, 1, 0. And you saw a current surge. So I charge the capacitor. It is charged now. The voltmeter doesn't show very much, 1500 volts. Maybe it went up a little, but not very much. But now I'm going to increase the gap to 7 millimeters. And look that the amp meter is not doing anything. The charge is trapped, so there is no charge going to the plates. But look what the voltmeter is doing. It's increasing the voltage. It's now approaching almost 10,000 volts, although this is not very quantitative. And now I have a gap of about 7 millimeters, and that's what I wanted. You've seen that the plates on the left side here are now farther apart than they were before. So that is my demonstration number 1. A repeat of what we did last time. So now comes number 2. So now my initial conditions are that V is now 10 kilovolts. So that's the potential difference between the plates that I have now. And D is now 7 millimeters, and I'm not going